We're continuing our quest for quantifying properties for substances that might change phase. In other words, they might be a compressed liquid, saturated mixture, saturated vapor, superheated vapor. And in this video, we're going to talk about substances that fall underneath the dome. In other words, they're saturated mixtures of liquid and vapor. So let's go ahead and get started quantifying. This particular video, I'm going to introduce you to the definition of quality, which is a property, but it's only defined underneath the vapor dome. So let's review about what we know about the vapor dome already. So remember, here's our green line is the tried and true vapor dome, right now depicting for H2O. On the y-axis is pressure, x-axis is specific volume. And also, I sure hope now in your mind, you've got a mental picture of phases associated with the vapor dome. So if you're laying on the left-hand side of the vapor dome, you're saturated liquid. If you're laying on the right-hand side of the vapor dome, just right there along the line, then you're saturated vapor. If you're underneath the dome, you are a saturated mixture phase. In other words, it's a mixture of saturated liquid and saturated vapor we just talked about. Now, of course, if you're to the right of the dome, you're superheated vapor. To the left of the dome, you're a compressed liquid, which will be a lot like tap water or compressed water. But in this video, we're going to talk about substances that are phase change substances that are laying underneath the dome. Okay, so what and where is a saturated mixture? So I'm trying to depict this in the PV diagram, so in the shaded area underneath the dome, trying to show you a little picture of what would it look like. Well, here's boiling water on the stove where you can see with your eyes a mixture of liquid and vapor. And so here's what I've come up with, somewhat formal definition. It says a saturated liquid vapor mixture is comprised of a proportion of saturated vapor, and the remaining proportion is saturated liquid. And I've tried to put down a little jargon list anticipating what folks might call the saturated mixture that you would find underneath the vapor dome. So a saturated liquid vapor mixture would be one way. Some people might just say liquid vapor mixture. You have to realize it's the same thing. Some people might call it a two-phase saturated mixture. That's perfectly valid, right? The two phases are liquid and vapor, or simply a two-phase mixture. So any of those can work. I try to say saturated liquid vapor mixture. That's what I try to say. And now for a formal definition of quality. And so we'll look at the definition, and then we'll come back and look at these text boxes up a little higher. So the formal definition of quality, X. So little x, that's the variable we're going to use in this class for quality, little x. And it's defined as in the mixture. So for a mixture of saturated liquid and saturated vapor, applying to a pure substance, we've got in the numerator, it's the mass of the saturated vapor part of the mixture divided by the total mass of the mixture. Okay, so I'm going to say it again. So the definition of quality, X, is the mass of the saturated vapor divided by the total mass of the mixture. Okay, so we want to take it one step further then. We think about what we've got. Numerator, the mass of the saturated vapor divided by, let's see, denominator. Well, the denominator is made up of two things, isn't it? The saturated liquid plus the saturated vapor masses. Okay, so if you think about this, if you've got 100% saturated vapor, if you're laying on this line here to the right of the critical point, your saturated vapor What is X there? X is 1.0 when you're laying on this saturated vapor line. How about to the left of the critical point? What is X over here? Well, if you're laying on this line, there is no saturated vapor, is there? So you've only got saturated liquid. So that means X equals 0 over here. Okay. And so some other kind of course, mathematical, just sort of details, right? X can only be a number between 0 and 1. It can never be less than 0. It can't be a negative number. And X cannot be greater than 1. And so this is kind of an important text box up here where X, the property X, quality, is only defined underneath the vapor dome. So out here, there is no such thing as X. And over here to the left, there is no such thing as X. So be very aware of that. If you get a value of X greater than 1, you've made some blunder. So that could be a good common sense check for you. Let's go a little mental exercise and apply some common sense 101. You see from my Pyrex bowl that's on the stove, water's boiling, I've drawn a little dash line to try to show, oh, here's my closed system, that, dash line, closed system. So I've kind of scoped out that volume there as a closed system. And the question would be, can you estimate the quality for this image? Can you estimate the quality for that right there? Think about that. About how would you quantify that with what you see? Would you say that the quality X is close to 1.0 or close to 0.0 or absolutely no way to tell at all? So remember, what's the definition of quality? The mass of the saturated vapor in the mixture divided by the total mass of the mixture. Okay. So, of course, I hope you have in your mind that you would be able to weigh this mixture, right? You could somehow imagine in your mind taking this thing off the stove and putting it on a scale. You could measure the mass of that mixture right there. It'd be easy to do. So you can get the denominator. What do you figure would be the mass of the saturated vapor floating around in this mixture? Do you think those little bubbles of steam, if you added up the mass of all those steam bubbles, what do you figure you'd get relative to the denominator? Don't you think that, doesn't your common sense tell you that by looking at that, you're going to get a very, very low value of X? The mass of the saturated vapor that you can see with your eyes is going to be a tiny number compared to the total mass of what's there on the stove that's mostly water. And so my common sense would tell me that X, for what we're looking at, would be a very, very low number, close to 0. So that would be my answer, close to 0.0, tiny little fraction. Okay, so there's the answer. Extremely low value, very close to 0 is what X is going to be. So I think you could kind of think that if you can see that, if you can visualize that in your mind. So where would we put it? Where would our X state be underneath the dome for this little mental exercise that we're looking at? It would certainly be around where the red dot is. Now we can't quantify exactly where it is, but do you see that you're close to saturated liquid because X is close to 0? So over here, when we're touching the vapor dome, X is 0.0. Over here, X is 1.0, saturated vapor. And of course, then I've labeled my pressure and temperature here because I'm on the stove here on Earth. I'd say my temperature is about 100 degrees C and my pressure about 101 kPa, give or take a little bit. It kind of makes sense to you? I hope that makes sense. Okay, now for an example problem. We're going to work out an easy numerical example problem. I'll try to chase you to some other videos, I think. But here's an example problem, and a heads up. we want to determine the quality X for H2O, water, when the temperature of the mixture is 200 degrees C and the specific volume is 0.1 cubic meters per kilogram. So we've got two properties. And the heads up that I have for you is this is such an easy problem that this problem is, it might be an early homework problem assignment in chapter 3, but very quickly you're going to start having homework problems that put it all together, and this little problem is going to quickly become a part of a much larger, more complex homework problem. So be aware of that you're going to have to master this skill quickly, because pretty soon your homework problems, this is just going to be a tiny little part of a much larger and more complex homework problem. Okay, so let's do this easy problem. We've got temperature given, and we've got specific volume given, and our job is to find X. How will we do that? Well, we're going to use the PV diagram to advantage. So let me try to step you through what we're going to do. All right. Now, temperature and specific volume are always independent intensive properties. So when you have a pair of data, temperature and specific volume numerically, you can get all the other properties you desire. Okay, so you're not going to have to check on this. So you don't have to check for the phase. And of course, it says find the quality. So you're going to hope that I'm not trying to pull a trick on you, that this V is going to be underneath this dome somewhere. So let's see, looking ahead, we're going to go to the temperature table, because temperature is given, and we will look up V sub G and V sub F. And by golly, this V, our V, is going to need to be in between those two numbers. Make sense? Okay, so I think I just said this, didn't I? Yikes. So we're going to go to our temperature table in the back of the book. We're going to find 200 degrees C, and we're going to write down VF and VG. And so from the previous video, don't forget this in SI, don't forget this tricky column heading. Saturated liquid VF times 1,000. VF times 1,000. So this number 1.1565, that is not the specific volume. You have to slip the decimal place 3 places to the left to get VF is 0.001165 cubic meters per kilogram, and then simply write down VG is 0.1274. Okay, so I'm feeling better. Even just with my eyes, I can see that 0.1 is in between these two numbers. So we're under the dome. So, okay, so let's see where we're at. We will draw our PV axes. Next thing we do is we draw a vapor dome. You see how it's not symmetric. It's kind of steep over here and then flattens out over here. Then we draw in a line of constant temperature. Just draw in a dogleg line. Be sure that this line is horizontal underneath the dome. In other words, pressure and temperature are dependent variables under the vapor dome. That's why this line is horizontal. And then once you're in the superheated zone, the temperature line starts to just lazily decrease down, kind of in line with the dome. All right, so that's this dogleg line here is a line of constant temperature, also known as an isotherm. So let's label our isotherm 200 degrees C, and we know we've got to lay on that dogleg line somewhere. Okay, we've just plopped down numbers for VG and VF, and here they are. And our number is 0.1. Wow, okay, so there we are. So the phase for water or steam water mixture at 200 degrees C is 0.1. And so we have just verified it is a saturated two-phase mixture. And now our job is to find the quality. I'm going to take you through the math on how to do that. Okay, so there's two ways to do this. So first is there is I'd hate to say it, a formula in the book. But let me try to discourage you from just blindly using a formula in the book and try to visualize what you're really doing. Okay. Do you see that? Let's see. It's the proportion of vapor divided by the total mass. Vapor mass divided by total mass. And so here's this formula in the book. It says you can show that the quality is V minus V sub F. That's going to be, you can show that that is going to be the mass of the vapor divided by Vg minus Vf. That's going to correspond to the total mass. Okay. And so what you're looking to do here is determine, look at the numerator. It's this amount right here. Okay, see how it's that amount. The denominator is Vg minus Vf. Okay. So do you see that what you're trying, X is a proportion. If this distance Z1 was all the way over to here, the numerator and the denominator would be the same, and X would be 1. If you're perilously close to here, X would be almost 0. Okay. And so so I'm hoping that when you can see this is derived. I was just thinking in my mind, I was multitasking and said, maybe I should have derived this expression in this video, but clearly I have not done that. I have not shown that the mass of the vapor can be expressed by this and the total mass can be expressed by that. So I'll have to apologize for not deriving that flat out. So let me try to chase you back to your book so that you can get the derivation of this X expression here, although you still remember that X is the mass of the vapor divided by the total mass. So I'll have to apologize for that. But now that we've got this fundamental relationship, do you see that this numerator is basically visually this distance here, the denominator is visually this distance here, and so almost by inspection, we've labeled V as 0.1, so we've got 0.1 minus the tiny number, that's the numerator, and then 0.1274 minus the tiny number, that's the denominator. So we'll turn the crank and get X equals 0.783, and we'll write out in English words the result. The quality of the saturated mixture is 78.3%. And you see that our sketch is pretty good because I've got this dot much closer to this numerical value than to this numerical value. So we're in pretty good shape, and that's the solution right there. Now I'm feeling guilty for not having shown the derivation for how do I get to that point. So all I can do is say, shame on me. And it's a good thing you have your textbook to fall back on to get to this result. Okay, and so despite my poor practice in not deriving that, you start with this definition, X, the quality, only under the dome, is the mass of the vapor over the mass of the mixture, and then recognize then the denominator can be expressed, mass of the mixture is mass of the vapor plus the mass of the liquid. Quality X is always greater than or equal to 0 and always less than or equal to 1. When X is 0, the phase, it's not your mixture anymore, your saturated liquid. When X is 1, your phase is saturated vapor, it's not a mixture. And then finally, the important thing to recognize is quality X is only defined underneath the vapor dome. So we blazed through that, and one reason we blazed through it was I didn't bother to derive that expression for quality using the specific volumes. So sorry about that. Please check out your textbook to get that derivation. Coming up in the next video is a reminder of what is internal energy, a new definition called enthalpy. That's going to be a new property that we will define. And then I'm going to try to show you some ideas on determining internal energy and enthalpy for phase change mixtures and phase change substances. Okay. Hope that you join in and have a look at that next video so you can start getting good at evaluating internal energy, a property that you have heard about already, and enthalpy, which is going to be a new property that we'll define here in the next video.